actually, this work was inspired by our earlier work on Graviton. So I'm very excited that I'll be telling you how we infuse confidential computing extensions into a custom AI accelerator. And we did this back in 2020. So it took some time before we were able to publish this work. So let's get started. So in the recent years, we have experienced a new wave of AI innovation. And as Marcus said, we can't do that without GPUs, which are required for cost-efficiently training these large models. Now, cloud, however, is a double-edged sword when it comes to confidentiality requirements of these AI workloads. The more you share, the more sophisticated attackers can steal your data. So we really need strong security mechanisms for preserving AI privacy in the cloud. Now, that's where confidential computing comes into the rescue. For those who are not familiar with this new paradigm, confidential computing introduces the concept of a trusted extension environment. We call that TE, to provide strong protection against privileged attackers, including hypervisor and operating systems. So this bases on the assumption that the tenant is willing to trust the hardware. And the hardware, in turn, gives the tenant a way to gives the tenant the ability to create secure environments where they can host their most sensitive, privacy-sensitive code and data. Now, in order to bootstrap these environments, the hardware provides a mechanism called remote attestation, which allows the tenants to verify that they're talking with an environment that hosts their code. And only then they will transfer the data into that environment. And we've seen major support by CPU vendors over the past 10 years. In fact, the support has evolved from protecting one process to protecting entire VMs. And unfortunately, we've seen, prior to this work I'm describing, we've seen limited support in PCI devices, mainly in the form of research proposals, including our work back in 2018. Very recently, we heard about NVIDIA announcing NVIDIA Hopper GPUs with confidential computing extensions. They're great. They work in conjunction with VM-based TEs, like the ones from AMD and Intel. But I believe that they come with large TCPs, right? You have to trust entire runtimes, entire device drivers, OSs, and that's quite bad for a tenant to decide whether they need to trust. You go from trusting a kernel, you need to trust the entire system. So we really want to provide a solution to this. So we want to design a low TCP TE that allows the tenant to decide whether they want to trust the CPU or not. And this is what we built in 2020. I'm showing here the development board we built that we manufacture using TSMC 7 nanometers. So this is work done with Graphcore, as I said earlier. So what we try to provide here is strong security guarantees. We isolate the entire device from the host. We added remote attestation using the hardware root of trust. And we were able to provide low performance overheads while providing without any changes to the programming model and without any trust in the CPU. So before I dive into more details about the trust extensions we added to this device, I'll introduce the Graphcore IPU architecture because most likely people are not familiar with it. Okay, so IPU stands for Intelligent Processing Unit. It's a quite massively parallel machine. As you see here, it employs thousands of tiles. And each tile is an in-order multi-threaded core with specialized units for AI. And unlike CPUs and GPUs, which employ deep-level memory hierarchies, which are bad for side channels, this IPU device employs a flat memory space. So each core has its own private SRAM, and this SRAM is mapped to this address space, so it can access it directly with loads and stores. Additionally to compute and memory, there is, of course, a PCI complex component which mediates the IPU host communication by serving two roles. So first, maps the host memory into the tiles address space by programming page tables, by allowing the host driver to program page tables, and also maps IPU memory into the host using PCI bars so that the host is able to program this device. So speaking of programming this device, how do we execute an AI workload? Well, if you are familiar with AI workloads, they fit really nicely into BSP paradigm. All they do, they fetch data, like a batch of samples. They compute. You need to exchange data between parallel units. And then you consume more data. You do more compute until you hit your convergence criteria. Now, having such well-defined phases is great from security perspective because we're able at the compilation time to construct IPU binaries that define the entire control data flow of the application. And this is great for security because the runtime and device drivers have minimal involvement during execution and can be removed from the TCP, as I will discuss later. So I think that the important bit here to understand is how do we fetch data into this device. So I'll talk more about external I/O. So the IPU software stack, which comprises the compiler and the runtime, introduces this abstraction of streams. In essence, the compiler takes input and output feeds. So think about like a TensorFlow graph. It takes the input and output feeds and map each one into a unique stream. And then it generates code that is part of the IPU binary that is triggered upon external synchronization events and generate DMA requests into host memory to fetch the data that it likes. Now, we also need support from the runtime in the flavor that the runtime needs to map a DMA buffer into the host memory, program the page tables so that DMA buffer is mapped to the address space of the tiles, and then populate this DMA buffer with data for every external synchronization event. So, and then the IPU binary is able to pull the data straight into their on-chip memory. Okay, so I mean, if you see this path here, it's vulnerable to quite like a malicious host controlling the stack, either compromising the device driver, or they have physical access to the memory or the PCI bus, or by just tampering with data directly in IPU memory. So on this note, as all security papers, we need to make assumptions about the threat model. Our threat model introduces a very small TCP. The hardware includes only the IPU and the root of trust, including the firmware, while the software includes only the ML framework. That's where you write your training script, and the IPU compiler that translates that script into code that executes on the device. So under this threat model, we wish to provide confidentiality and integrity of both data and computation. And we leave out of scope physical sidechain attacks, just like differential power analysis and package manufacturing attack where manufacturers install backdoors into the device. OK, so next I'll talk a bit more about IPU Trusted Extensions. I don't have the time to go over the details. So I'll try to describe this at a high level and dive into important bits. So, but the paper, I mean, you can read the paper if you're interested in finding more about the design. All right. So as I said earlier, we want to remove the trust from the runtime. So the first step is to prevent that runtime from having access to plain text data. So the way we do this is by decoupling the compilation from execution. So what that means is that the tenant who was to use the device in the cloud, they have access to the tool chain, and they can actually take the TensorFlow graph or PyTorch, whatever you like, and compile the application binary, and pre-process the data set in the shape that the application binary needs to consume it. And then they just encrypt their code and data and ship it into the cloud. So all the runtime sees here is ciphertext. Of course, the runtime needs to populate these DMA buffers. How does it do that? So the compiler generates also a job manifest, which instructs, which has information what data needs to be populated for every synchronization point, and also includes, you augmented this job manifest also include information that need to be enforced by the by the root of trust, as I will describe later. So, okay, so we have encrypted code, the data. I mean, we need to provide low performance overhead, so it's natural that we added AES-GCM encryption engines into the PCI memory path, so they intercept the packets so they can decrypt and encrypt. We were able to deliver this at the PCI Gen 4 bandwidth rate. Of course, you add silicon, but we were able to do it with just like less than 1% of the silicon. We added a hardware root of trust. We call it confidential compute unit, which is responsible for managing the lifecycle of the TE and attesting the code using the job manifest, and then provisioning keys after remote attestation, after the verifier, remote tenant verifies the device. So I'll tell more about how we do the attestation, but also another important component that we added is this trusted mode, which is set by the CCU during the TE creation. And based on the observation that training jobs span lots of devices, right? We'll talk about hundreds or thousands of accelerators. Our TE spans the entire device. And this is great for security because the less you share, the smaller attack surface you have. And also, it blocks the host from accessing the IPU, as well as security-sensitive PCI registers. All right. So now, I think the natural question is that if you have a device that is in an isolated mode, how do you bootstrap execution? And in order to bootstrap execution, you need to deploy the encryption keys to decrypt the IPU binary and the data. But also, you need a way to load the IPU binary, given that the host no longer has access to the IPU memory. So first, the runtime asks the CCU to launch the T, and basically just passes over the job manifest. And as I said earlier, the job manifest includes information about the key identifiers that it needs to load, the keys identifiers for keys that need to be loaded for each stream, but also includes information about the application binary in the form of a hash. So basically, it says that the hash of the expected binary is like SHA-256, right? So once the IPU binary has access to this job manifest, what it does is to issue an attestation that is routed to an attestation key that it's rooted to a unique secret that has been provisioned during manufacturing. And the provisioning works like the same. The root of trust itself samples enough entropy from the device to actually to provision that key. So these keys are not known to any outsider except for the device. OK. So once we have this attestation that captures security properties, the hash of the job manifest, we send it over to the remote verifier. They verify that this attestation is genuine and as expected, and they establish a secure channel with the CCU, and they transfer their keys. So the keys are now in the cryptographic engines. How do we bring the application binary in an efficient manner? And that's what we rely on the CCU to deploy a small application, which is going to load the IPU binary from the DMA buffer. And the IPU binary will be decrypted as it comes from over the PCI bus. Right. So once the IPU binary is there, then it can go and fetch data to execute the application. Now, while the runtime cannot see any plain text data, it is able to tamper with computation by reordering or replaying data in these DMA buffers. So in order to avoid this, we rely on a novel encryption protocol for DMA. And we just, again, rely on the observation that the compiler has a full view of all the data that need to be processed by this IPU application. And the compiler, we modify the compiler to map all these streams into an address space and partition each stream into frames that will be encrypted using standard crypto libraries. Now, each frame can be identified using a unique identifier. And because the streams are write-once abstractions, that means that each frame needs to be encrypted only once. And as you might know, HGCM works really well if you can guarantee that the IV is not reused across different frames for the same key. But because these are write-once abstractions, as I said, we can reuse this identifier as an IV during encryption. And given that we're talking about an explicit IV encryption protocol here, where the encryption engines don't have access to that IV, we need an efficient way to supply that. So what we did is that we added that as part of the header of the frame. And then we can rely on the decryption engine to ensure integrity based on the tag. But what the decryption engine cannot verify is whether the IV corresponds to the packet, to the frame that the IPU binary asked for. But we can rely on the receiver, which is the IPU binary, to verify that indeed that IV matches the identifier they requested for. So this way, we have a low-cost protection against replay and reorder attacks. So it's unlike SGX, which required expensive multi-trees to protect against reorder replay attacks for memory. This is a very cheap solution to achieve the same guarantees. We have more details in the paper, so I encourage you to read if you're interested. So I'll quickly wrap up this talk by showing a few results. As I said, we built this in 2020. We had a development board using engineering examples operating at 900 megahertz. Back in the day, ResNet was a huge model for the ML community, but especially for Graphcore. So we used ResNet on C410. And then after we decided to publish a paper about this work, we compared the performance of proposed hardware against the VM-based T, just to confirm that we can still get the accelerator-grade performance provided by the accelerator. So I have one graph, and this graph will plot a set of bars for each workload. The first bar is going to be about the overhead we have over baseline IPU. And the second bar will just show the gains over VM-based Ts, like AMD SFSMP. So here I'm showing like overheads ranging from 3% to 18%. And we found that the ITX overheads for small models like ResNet 56, which was taking like a few minutes to run on the IPU, were dominated by the startup costs, including creating the T and deploying keys. For larger models, we saw, larger models with codes, right? Because this model was just taking half an hour, given that how big models we have today. You can say this is a small model. But even for such models, the overheads of starting up the T were well amortized. And the total runtime overheads were around 3%, mainly dominated by the runtime encryption overhead. All in all, we were able to deliver huge performance gains over CPU Ts, which is great because we can get strong security guarantees, even better than CPU Ts, but while maintaining the accelerator-grade performance. To conclude, I really believe that, in the near future or for the foreseeable future, we will need infrastructure for hyperscale privacy-preserving AI. And in this work, I showed you the first ASIC that enabled high-performance confidential AI with strong security guarantees, low TCP without trusting the CPU, and low performance overheads. Since then, we've seen support by the AI ecosystem, mainly NVIDIA GPUs. But we really hope that our work will serve as a blueprint for future confidential computing hardware. Thanks. I'll take questions.